Welcome. In this session, we'll begin our look at higher order derivatives. If f is a differentiable function, then we define its derivative, which is another function, f prime. If f prime is also differentiable, I can talk about its derivative. Starting with f, we differentiate two times, so it's called the second order derivative, or very often in shortened form, second derivative. Same way we can talk about the third order derivative, fourth order derivative, so on. The prototypical example of second derivative is acceleration. The first derivative of distance is speed, and the derivative of speed, the rate at which speed changes, is acceleration. So the second derivative tells how fast you are accelerating or perhaps decelerating. Third, fourth derivatives, etc. don't have that good an interpretation. Geometrically, the second derivative tells us how the graph bends, in other words, how much it differs from a straight line. If the first derivative is constant, it turns out the function must be linear. So in that case, second derivative is 0. So this aspect of second derivative we will see in the next chapter under the heading of concavity. For now, we will just look at techniques of calculating it, which really is nothing new. It's just a matter of combining or repeating the differentiation process using the rules we've already seen twice. We also need to set up notation so that we can indicate higher order derivatives concisely. If you use the prime notation, the convention is very simple. You just put one prime for each derivative. But this is kind of hard to read and also easy to miscount number of primes. So with third and higher order derivatives, the convention is to put the number of times we differentiate in numerals. So the third derivative I will write as f and then 3 inside parentheses as a superscript. Fourth derivative will be f, 4 inside parentheses as a superscript, so on. The Leibniz or differential notation takes some explaining. We can think of the differential notation as a fraction, but also as applying the operator d over dx to a function f. So second derivative means we apply d over dx to the result of d over dx applied to f. So it's d over dx and then d over dx within parentheses. So it's like I have d over dx, and then f. The numerator I have d and then d, I write it as if it's d squared. The denominator I have dx and then dx, I write it as if it's dx squared. Of course, these are not really squares. It's just a convention we use. The third derivative would be written as d cubed x over dx cubed, so on. Of course, these two numbers should always be the same. In chapter 17, when we do partial derivatives, it won't quite work that way. So even though this notation looks redundant at this point, it's not always so. So we will stick with this in the interest of future expandability, future adaptability. Of course, finding higher order derivatives is just a matter of knowing how many times to differentiate. Let's start with a polynomial. So we'll go ahead and calculate all higher order derivatives. Here I have a polynomial 2x cubed minus 5x squared plus 11x minus 21. Differentiating polynomials is easy. You just differentiate term by term using the power rule. So here I get 2 times x cubed or 6x squared minus 5 times 2x or minus 10x plus 11, and then minus 0. The second derivative is the derivative of the first derivative. So the second derivative is the derivative of 6x squared minus 10x plus 11. That's 6 times 2x or 12x minus 10. Third derivative is the derivative of the second derivative. That's just 12. Since it's a constant, the fourth derivative is 0. Of course, once you hit 0, it's 0 from then on. It turns out only polynomial functions have this property. if you take a function that's not polynomial, the higher order derivatives don't get simpler. In fact, very often they get worse. The expressions get more and more complicated. So it's a good thing we don't often have to do anything more than the second derivative. Let's find the second derivative of a rational function. In this case, I have 2v over v squared plus 1. First derivative, I just use the quotient rule. So the numerator is 2v, its derivative is 2 times denominator v squared plus 1 minus the numerator 2v times derivative of the denominator. Denominator is v squared plus 1, its derivative is 2v over square of the original function's denominator. So over v squared plus 1 quantity squared. Since I need to differentiate this again, I'm going to simplify this just a little bit by simplifying the numerator. Let's distribute the 2 in the first term. So that's 2v squared plus 2. And then in the second term I have 2v times 2v, that's minus 4v squared. And then combine the two like terms, 2v squared minus 4v squared is negative 2v squared. I still have a fraction, so I'm going to use the quotient rule again to differentiate the first derivative, that is the second derivative of the original function. So in the first derivative, the numerator is 2 minus 2v squared, its derivative is negative 4v, times the denominator v squared plus 1 quantity squared, minus the numerator of the function I'm differentiating, 2 minus 2v squared. The denominator have power of a polynomial, so I have to use the power rule and chain rule. First differentiate for the exponent 2, which gives me 2 times v squared plus 1, and then differentiate the inside. The inside is v squared plus 1, its derivative is 2v. The whole thing over square of that denominator, so square of v squared plus 1 quantity squared. Of course, we can simplify this a little bit, and I should really do that if we want to find the third derivative. But since all it asked for is second derivative, not even simplified, we can just stop here.